The goal now is to learn how to manipulate multi-qubit registers. All valid quantum operations are given by unitary matrices. What does it mean for a matrix to be unitary? Remember, this means that U needs to verify that U times U dagger, that is U times its conjugate transpose, must be the identity. Equivalently, we can define U as a unitary if it preserves inner products. First, let's take a look at gates for 2-qubit registers. In the case of 2 qubits, the gates will be given by unitary 4-dimensional matrices. So, the most trivial type of 2-qubit gate consists of a 1-qubit gate on each of the qubits. For example, we might apply an X gate to the top qubit and an H gate to the bottom one. We call such a gate a product or composite gate. The matrix associated with this gate is simply the tensor product of the individual gates, in this case X and H. However, if we think of a circuit that starts in a product state and applies independent gates to each of the qubits, that can't possibly generate entanglement. So, there are other gates or matrices that can take a product state into an entangled state. Consider, for instance, the following gate. In order to define its action, it is sufficient to give the action of the gate on all the elements of a basis. Here, we can see the recipe for a gate that flips the bottom qubit only if the top qubit is in state 1. We call this gate a C-node, which stands for control node, where the top qubit controls whether we flip the bottom qubit, which is called the target qubit. For analogous reasons, this gate is also sometimes called a control X gate. So now let's look into the matrix representation of this gate. We want 0, 0 to go to 0, 0. This gives us the leftmost column of the 4x4 matrix that represents the C-node. We want 0, 1 to go to 0, 1. This gives us the second column of the matrix. Finally, 1, 0 goes to 1, 1, and 1, 1 goes to 1, 0. And this completes the matrix. We've said that the C-node gate allows us to create entanglement. Let's see how. If we apply the C-node to the state plus 0, we create the state 0, 0 plus 1, 1, which you might recognize as one of the Bell states. In fact, by choosing the appropriate input states for the top and bottom qubits, we can create the 4 Bell states.